Now that we've seen a little bit of a light intro to systems, let's continue with our light introduction to systems to see some systems that we've already seen before and try and understand what we mean by system properties in light of those systems. So basically, we'd like to look at these simple systems such as gains, delays, and timescaling and modulation, and use block diagrams to represent those systems graphically. So we've seen a few simple systems before in this class. We've seen a simple gain, which we indicate with a triangle with an alpha in it, and so that just means take x of t and multiply it by alpha. We've also seen a delay, and I write delays as delta of t minus tau, and that's because when we study linear and time invariant systems, we'll see that that's the important way to do it. We could just think of this as a delay of tau, though, if you want to write it that way. We also have this scale, time scaling, so x of t, we can get x of alpha t if we scale the time axis. And then this last operation, which we call modulation, which is multiplying x of t by another signal, in this case a cosine. And the cosine is at omega ct. C is called the carrier frequency. And so this is, for example, what happens in AM radio. You're modulating. AM stands for amplitude modulation. You're modulating the amplitude of a cosine wave. For discrete time systems, we also saw some of these examples, the simple gain as before. We also had this delay. This time we wrote it as z to the minus k, which is going to come up when we talk about z transforms. So we can just think of this again as delay of k if you prefer. And then we have the upsampler and the downsampler that we saw before. And those are also examples of systems. Systems are defined by this input-output relation, we call it. So we want to know then, given an input-output relation for a system, which is just like a way of writing y in terms of x, so what kind of properties do we want to know about that mapping from x's to y's? So the first might be we want to know, how does y depend on x temporally? That is, at time t, does y depend only on past values of x and the current value of x, or does it depend on future values of x? Now, it might seem weird to design a signal that depends on the future, but think about offline signal processing. If you have a recording, you might process it offline, in which case, if you want to look at, say, putting an output at time 3 seconds, the output at time 3 seconds can depend on stuff like, say, between 3 minus a half and 3 plus a half seconds. So that's okay, and that system wouldn't be causal, but it would be still a perfectly useful system to run. However, many systems we want them to be causal, and that's because we want to be able to plug them in and have them work in an online way. If you want a system that works in an online way, you need to have the output be a function only of past inputs. So what about stability? So stability is pretty straightforward. If there's an input which makes the output blow up, a nicely behaved input that is bounded that makes the output blow up, then it's not stable. And so we like to deal with stable systems. And sometimes there exist systems that we like to build that they work well on paper, but they're neither causal nor stable, so we can't necessarily build them in a circuit, in which case we call them not realizable. Linearity and time invariance are two important properties which go hand in hand. In most of the class, we're going to talk about linear time invariant systems. A system is linear, of course, if it's the superposition principle holds, where we can take a linear combination of the signals and we get a linear combination of the outputs. A system is time invariant if it behaves the same way, for example, today and tomorrow. So that is, if I take my function generator, put in a little sample signal into the system, measure the output, then if I run that experiment today and I run that experiment tomorrow, I'll get the same results. And time invariance is a really important property because it says that the system itself doesn't actually need to know what time it is, in absolute time. Lots of systems are time invariant, some systems are not, and it's important to be able to tell when one is time invariant and when one isn't. Invertibility we can think of is pretty straightforward. Is like, is there an inverse function? So is there an inverse system? So given that I have a mapping from x's to y's, from those y's can I get back the original x's? If the system doesn't really destroy any information, if you think about it, doesn't destroy information about x, then I can recover y. So for example, a system which is not invertible would be like absolute value, because then we don't know the sign of x. But lots of systems are also invertible, and so we'd like to be able to, say, then calculate the inverse system. However, this inverse system, as an example, might not be causal or stable, which are those nice properties that we wanted to have also before. Let's look at a positive gain A applied to a signal. So y of t is a times x of t. So what properties does it have? Well, at time tau, y of tau only depends on x of tau right at that time tau. So this system is causal. And if I look at it, the only way for y of t to blow up to infinity is if x of t also blows up to infinity. So if x of t is a bounded signal, then the output is always going to be bounded by a times the maximum value of the input signal, and so it's stable. Scalar multiplication is always a linear operation. It's pretty straightforward to show. And is it time invariant? Well, this actually requires some more mathematical proof, which we'll get into a little bit later. But looking at it, it doesn't seem to matter whether t is equal to 0 or t equals 10 to the third or anything like that. It doesn't depend on the absolute value of the time t. So this system is actually time invariant. And finally, we can just divide by a to get the input back. So this system is invertible as long as a is not equal to 0. Let's look at a simple delay in discrete time. So delay by k. So y of n is equal to x of n minus k. So at time n, y of n only depends on x of n minus k. So if k is positive, then this is some past value of x, so the system is causal. Or if k equals 0, it's the current value of x, so it's still causal. But if k is negative, then this is some future value of x, so then y of n would be what we call anti-causal. And this system would be anti-causal, that is. Note, in the same way, the only way for the output to blow up is if the input blows up, so it's the same as the gain, so this system is in fact stable. The delay is linear, so that satisfies linearity. And now we have to think about time invariance. So if I delay the if I delay the input x of n, if I delay it by L, so I put in x of n minus L, then I'm going to get x of n minus k minus L, and that's the same as the output at time n minus L. So delaying the input by a certain amount delays the output by the same amount, and that's actually how you prove that something is time invariant. As long as if you delay the input, you get the same delay in the output. So this thing is time invariant, and we can recover the input by using a delay of minus k. Note that if the delay is positive, so if, say, k is equal to 2, then I would have to use a non-causal system to invert, because I have to advance the signal by 2 to invert this delay. So mathematically, the system is this map whose input and output are both signals, so we can write it as generically as this map H. And so we're going to dig into these properties that I mentioned before and see what properties they can have and see some more examples. In the meantime, you might want to look at some of the properties that I mentioned, these 5 properties, for the other types of basic systems that we've seen already, and see if you can verify whether they hold or not.